Hello, welcome to Coffee Break with Microchip Technology. Coffee Break is our ongoing forum in which we discuss new and evolving technology, all in about the amount of time it takes to drink a cup of coffee. So welcome, I'm your host, Eric Glatfelter. Aliyah Fahout, our moderator, is with us also. Hello, Aliyah.
Hello, everyone. Thank you for joining us today. We are currently live on YouTube, Facebook, and LinkedIn. You can participate in today's episode by leaving your questions and comments in the chat or email us at livestream@microchip.com after the broadcast. Don't forget to follow us on LinkedIn and subscribe to our YouTube channel as well. Back to you, Eric.
Thanks, Aliyah. Our topic today is speed up dsPIC DSC motor control designs with a complete ecosystem. Joining us today is Patrick Heath, Marketing Manager at Microchip. Patrick, welcome to Coffee Break.
Thank you, Eric.
All right, so we're talking about motor drivers and motor driver designs. What are the latest design trends and design challenges that people are facing in the world today?
Sure, we're tracking two design challenges that we've been trying to help customers by working on. The first one is going to be talking about some applications that really have space constraints, and that we need a solution that integrates more into a single device in order to approach those applications. The second area that we've been working on is an area that is for customers that are using field-oriented control, but also need to have the full motor torque available at startup and at slow speeds. And so this has been a problem for FLC, and we have a new algorithm called ZSMT that attacks that problem.
Okay, well, let's talk about both of those. First of all, the applications. Can you give us some examples of extremely space-constrained applications?
Yeah, there's a lot of them. Automotive is a good area. So the first example we have is from automotive, and that's for an engine cooling fan or an automotive cooling fan. And typically, the radiator fan goes in the front of the car, and the control board for that fan has to fit on the back of the motor, of the fan motor itself. And so this is a very small space, usually kind of circular, round. And as you can see in the picture, the board is small, and there's really only room for the 6 MOSFETs and a single chip to control that. Mm-hmm. And so we've made an integrated motor driver chip that combines a dsPIC motor control device with a full bridge MOSFET gate driver and a LIN transceiver in one chip, so that we can attack this problem. And so you can see that using this, we can fit into the space.
Okay, and this is an area that's not going away with electrification, right? So you need this with an old-fashioned combustion engine, and you also need it with an electric vehicle.
Yes, that's true. Electric vehicles also need a cooling fan in the front. Even without an engine, they have a lot of electronics and motors that need to be cooled.
Okay, so obviously automotive is an enormous space. Are there other kinds of really space-constrained applications in automotive?
Sure, here's a second application. This is for a camshaft. This is used on a combustion engine, obviously, where you have a camshaft that's running and opening and closing the intake and exhaust valves. Mm-hmm. And in the old days, of course, this was run by a belt or gear train or something, but nowadays it's run by electric motor. And so the space for that electric motor is very small, and the space for the control board for that electric motor is even smaller. And so here you can see that the space, this little rectangular space, is very small, and they really only have room for the 6 MOSFETs and an integrated type of motor driver in order to solve the problem. And this one also has a CAN transceiver built in, because in the automotive world, a bunch of the motor control applications use LIN for communications, but
sure.
Some others also use CAN for communications.
Okay, and we have options for either
both,
of those
yeah.
protocols. Okay, what other kinds of applications, maybe industrial or consumer?
Yeah, here's an example for a stick vacuum cleaner. So stick vacuum cleaners, you want to be very light and easy to move, and,
yep.
and it's small. And so the motor is also very small. And again, the controller board for the motor for the vacuum cleaner has to fit onto the back, the top of the motor itself. So it's a round area, generally 40 or 50 millimeters in diameter. And so as you can see here, due to the small size of the board, we were able to approach that with an integrated motor driver on one side and putting the 6 MOSFETs on the bottom side in order to attack this problem.
Okay, so I think we can clearly see from those visuals in the description that we have very small boards, and we've got a device that has a lot of functionality packed inside of it to accommodate that. Can you tell us more about what's going on inside that package?
Sure. So in this case, for an integrated motor driver, what we're going to do is we're going to combine up to 3 dies. The first is a dsPIC digital signal controller that's really the motor control is running the field oriented control algorithm or whatever algorithm you want to use to control the motor. And right next to it, there's going to be a full bridge MOSFET gate driver, which will drive, the inverter for the three-phase motor. And optionally, we're going to either include a CAN or a LIN transceiver, depending on whether that's needed or not. But as we said before, in automotive, some communications require CAN, some communications require LIN.
Right. Okay. So we're talking about the hardware now, and we'll get to more of the ecosystem, but I guess the next step closely related to the hardware would be development boards. So we have some development board options for customers.
I did bring a board here, and so this board is for our integrated motor drivers development. And in the middle right here, you can see the integrated motor driver, which combines the dsPIC digital signal controller doing the motor control job with the MOSFET gate drivers. And so there's really nothing between it and the MOSFETs at the bottom of the board here. So that directly drives the 6 MOSFETs, and then the connection to the motors at the bottom in the green connector. So this makes for a really clean, small board design. Okay. And this development board is what we provide to customers in order to do their development.
Okay, and then we've got another option with the DIM module.
So for this board, which is for normal dsPIC devices without integrated motor driver, we have to have the MOSFET gate drivers on the inverter board. So you can see there's 3 MOSFET gate drivers driving the MOSFETs here, and so this makes the board slightly larger. And this is for normal dsPIC digital signal controller, motor control devices. And in order to configure those for each one, we provide a dsPIC on a DIM, a dual inline module, and that fits in very easily into the center of the board, and that personalizes the board for that particular dsPIC device.
Okay, so we have the host board, and then we have multiple options for the DIM module itself.
Yeah, currently we have released a production 5 of these dual inline modules or DIMs, and there's more coming.
Okay, great. So let's shift away from the hardware a bit. Let's talk more about the software. But before we do that, earlier you mentioned a design issue with needing to extract maximum torque at startup. So can you tell us more about that problem and what we offer to ease the design for customers?
Turns out there's lots of applications that need the full torque of the motor at startup or at slow speeds. And you can think about having an e-bike or e-scooter, and you're starting out and you're on a hill, and you need the full torque of the motor to go uphill, right? Or consider a drill where you have a bolt, maybe a lag bolt in a 2x4, and you want to loosen it. You need the full torque from that drill motor in order to get that bolt moving and loosening it. So, and there's many other application examples, but these are 2 good ones. And in order to solve that problem, you need the full torque of the motor at that moment. And for FOC, that's a problem for field ordered control. But we've added a new algorithm called zero speed maximum torque, or ZSMT for short, that can determine the position of the rotor at standstill, at startup. And because we know that information, we can provide the full motor torque at startup and at slow speeds until the speed gets up fast enough where field oriented control can close the loop and take over. Okay,
nice. So how would somebody access this algorithm?
So fortunately, we have a free tool called MotorBench, which is a GUI, and it runs on your PC, and it's part of the MPLAB X IDE. And it does 3 things. It will extract the motor parameters that we need in order to run field-oriented control. It will tune the 3 PI control loops for speed, ID, and IQ. That is what makes the basis for field-oriented control. And then it will generate the whole code that you need to run the motor from startup to running the motor. And now there's an option in version 2.45, the latest release, there's an option called to turn on and enable ZSMT in that tool.
Okay, and someone can download MotorBench from the website?
Yes, there's a link, microchip.com/MotorBench. You can go there and you can read about it, and if you're in the MPLAB X IDE, you can eventually download the free library.
Awesome. So what other trends are there in software development or otherwise in the ecosystem?
There is another trend that we've been watching, and that is for customers to use modeling and simulation, not only to model and simulate, but also to generate the code for their end project. Typically, they do this using MathWorks MATLAB Simulink environment, and we now support that with 11 different demo projects And
Okay.
you can find these on Microchip Discover or on MathWorks webpage.
Okay.
And these projects are template-based now so that you can easily switch between a different dsPIC device or a different hardware development board or a different version of the field-oriented control algorithm, model, simulate, and then generate the code and download it to the board and run the motor.
Okay. Nice. So it sounds like maybe if you don't have if you're not wouldn't consider yourself an expert in motor control, or if you're just looking to speed your design along a little bit, this would be a nice option.
Well, I think there's, there are some companies there, who don't have a large software development team or a lot of experience in writing software code. So this approach using Math and Simulink to generate the project code and go to production with it is another alternative where they don't really have to learn the code or know anything about the code in order to create it.
Very nice. Okay, so we've talked about hardware boards. We've got the motor bench. We've got some demo projects in Simulink. What else do we have for
What are we
customers?
missing? What are we missing? So we've also been working on something we call reference designs. These are boards that come with the design file for the board, the user's guide for the board, which includes the schematics and the bill of material, and also the source code for that board, for the dsPIC that's on that board to run the application.
Okay.
And so we made these reference designs. The first one we did was for a refrigerator, then we did an air conditioner, compressor and fan, a kicky scooter, and more recently we did a low voltage ceiling fan, which is not an ACIM fan, but a BLDC fan because it's more efficient. We have the engine cooling fan that we just talked about, and we just completed a drone propeller reference design. So these reference designs are on the web. They're free download of the design files, the user's guide, the source code, and they're really magical in allowing customers to see how to get from what we did to their end product very quickly.
Okay, great. Interesting range of applications there, and given the heat that we're experiencing, I expect we'll see lots of downloads on the air conditioner and ceiling fan options.
24 days of 110 degrees plus, yeah.
All right. Well, Patrick, thank you so much for bringing the boards and talking about them and sharing your expertise on this topic. At this point, let's go to Aaliyah and see if there are any questions from our viewers today.
Yes, Eric, we do have a few questions for you we received via email. The first one is, do the integrated motor drivers work over the automotive temperature range?
Well, that's a great question. So a lot of our business, maybe a third of our business, is actually automotive motor control. So everything we do is geared towards automotive, which all the other customers can benefit from. So yes, these devices are offered in three temperature ranges, including the H temperature range, which is for automotive.
Okay.
Great. I have a question via LinkedIn, and I know Patrick answered a part of this question, but is there a solution to have a driver on motor package? I have a concept design for this soon that I'm going to develop.
I'm sorry, read that one more time, the question.
So you did answer part of this question already, but is there a solution to have a driver on motor package? I have a concept design for this soon that I'm going to develop.
Driver on motor. That's an interesting question. We don't make motors here, so I'm not sure that we have the capability of actually integrating the driver onto the motor itself. But sure, we'd entertain that if someone brought a proposal to us, but that's an interesting idea.
All right, awesome. Another question I have for you is, does ZSMT support high voltage motors or just low voltage motors?
So ZSMT actually supports any motor that's low inductance. As it turns out, most high voltage motors are also high inductance. And that requires a slight change to our ZSMT algorithm, which we actually have now and we're working on, and we expect to roll that out. Probably early next year, we'll have a new version of ZSMT which supports high voltage, high inductance motors.
Okay.
Awesome. Another question is, besides the MCLV 48 volt 300 watt inverter board, are there other boards that use the new motor control DIMMs?
Yeah, we obviously want to get a lot of reuse of our DIMM design concept, and so we have a whole series of boards planned that will use these DIMMs, plug-in DIMMs. The next one, which is almost completed design, is a high voltage board, MCHV 230 volts, 1.5 kilowatt design. And after that, we plan a stepper motor, a control board, and then a multi-motor board that will also use the DIMM concept.
Great. And I think we have a time for a few more questions. This one's from the email as well. And it is, what new reference designs are in progress now?
Oh, see, reference designs are always very popular. So currently we've just started work on a new oil pump reference design, plus we're working on an e-bike and an e-motorcycle reference design. These are different from the Kiki scooter. The Kiki scooter is 350 watts. The e-bike will be about 1 kilowatt, and the e-motorcycle will be 6 kilowatt and above. So three different power ranges for e-mobility. Okay.
And then one more question I have for you is, how is this new board different from the MCLV2?
Well, that's a good question. So MCLV2 was the, this MCLV 48 volt 300 watt is actually the replacement for the MCLV2. It's more modular in that we've gone away from a square PIM to this dual inline DIM because the insertion force for the DIM is so much easier to insert and to pull out of the board than the square PIM was. And also, this has more pins. It's 120 pins versus 100 pins. So that's one advantage. The other improvement that we made is that we put all the user interface now accessible by these two connectors on the corner of the board. There's two Explain Pro connectors. One's populated, one's not. And using those Explain Pro connectors, a user can add another board to customize it, to add whatever features or expansion that they want to the board. So it makes a more modular approach for us.
Awesome. Well, thank you, Patrick, for answering our viewers' questions today. And the audience, if you have additional questions or comments, you can email us at livestream@microchip.com after the broadcast. And don't forget to follow us on LinkedIn and subscribe to our YouTube channel. Back to you guys.
Thanks, Aaliyah. Patrick, thanks again for joining us. Thank you to our viewers for taking some time out of your day to listen to our topic. Please visit us at microchip.com/coffeebreak. You can see our schedule for the remainder of Season 10. You can sign up for notifications, and you can peruse our library of previously recorded Coffee Break episodes. Thank you again, and see you next time.